parallel resonance. Consider this is a circuit and L and C are connected in parallel, but L inductance, L some ohmic resistance. This is a circuit diagram. Okay, here we have to connect AC source. For the AC source, it is this is L, this is R, and this is C. Record చేస్తున్నా. See, consider a parallel resonance which are one branch contains an inductor and small ohmic resistance R, and other branch contains only capacitance of a capacitor. So, as we know that, suppose we have to write equivalent impedance, admittance, impedance, which is equal to these two are connected in parallel, so therefore equivalent impedance is equal to Z1 plus Z2. Let us take Z1 is a impedance offered by the capacitor, as we know that Z1 is equal to 1 by J omega C. And similarly, Z2 is equal to inductor and resistors are connected in series. So therefore, the equivalent impedances is R plus J omega L. So therefore, 1 by Z equivalent is equal to 1 by Z1. Z1 means 1 by J omega C plus 1 by Z2. So 1 divided by Z2 is R plus J omega L. So therefore, this becomes J omega C plus 1 by R plus J omega L. This Z equivalence can be written as Y equivalent also. Admittance is equal. So what happens is, now here Y equivalent is equal to J omega C, and place this denominator, it has a complex quantity, so therefore I'll rationalize this quantity. That becomes R plus J omega L multiplied rationalization R minus J omega L divided by R minus J omega L. So therefore this becomes J omega C plus R minus J omega L divided by this A plus B into A plus B into A minus B. So therefore this can be written as R square minus B square. But in this J square is there, right? This J square is equal to minus 1. So therefore minus of minus will become plus omega square L square. So further this is J omega C plus R by R square plus omega square L square minus J omega L divided by R square plus omega square L square. So here I'll separate real and imaginary parts. This real part R square plus omega square L square plus I'll take a J common. So this becomes omega C minus omega L divided by R square plus omega square L square. So this is Y equivalent. So this can be written as, this is real part conductivity plus J susceptibility. Y is equal to, here for resonance, at resonance condition, this B susceptibility of this parallel circuit becomes 0. So therefore omega C minus omega L divided by R square plus omega square L square is equal to 0. And further, this is omega C is equal to omega L divided by R square plus omega square L square. If I cross multiply, this is omega c r square plus omega q L square C is equal to omega L. This omega here, 1 omega, this omega get cancelled. This is C R square plus omega square L C. L square C is equal to L. So omega square L square C is equal to L minus C R square. So therefore omega square is equal to L divided by L square C minus C R square divided by L square C. Now C get cancelled. This L and square get cancelled. So omega square is equal to 1 by LC minus R square by L square. So what is omega? Omega becomes under root. So therefore, what is omega? 2 pi f. So therefore, FC, this is FC, omega c. At this condition, this omega will become omega c. So therefore, this becomes cutoff frequency, which is equal to 1 by 2 pi under root of 1 by LC minus R square by L square. This is the resonant frequency of parallel resonance circuits. This is a parallel resonance circuit. Simple. Here, what I did here is I took L and C circuit. See, this is a parallel branch of L and C only, but this the coils has some resistance value or this is called as an ohmic resistance. Ohmic resistance. Here in this case, we consider this capacitor doesn't have any ohmic resistance. So therefore, this ohmic resistance R value is 0. You consider. So here applied a voltage B. Here a sinusoidal signal we need to apply at one instant of time at one particular frequency. This particular circuit is going to be resonate. So therefore, for this, at what resonance means, first of all, for this parallel circuit, we have to calculate equivalent impedances. You know that when two impedances are connected in parallel, this equivalent principle. See, this is this is a branch 1 and this is a branch 2. This is branch 1 and this is branch 2. So branch 1, the impedance offered by the capacitor is equal to 1 by j omega c and impedance offered by the Z2 is equal to R plus j omega L. Why? Because these two are connected in series. So therefore, 1 by Z equivalent becomes 1 by Z1 is 1 by j omega c and Z2 is R plus j omega L. I'll substitute it here and make a rationalization. This is rationalization. Rationalization. So after this converted here, and later I separated this is a real part and this is an imaginary part. At resonancy, this imaginary term has to be 0. Why? Because at resonance, both voltage and current should be in phase. That situation happens only because of this imaginary quantity. This quantity is responsible for phase changes in the this parallel circuit. So if it is 0, that condition is considered as a resonance condition. So therefore, if this y is equal to g plus jb, this is a conductivity plus j susceptibility. B is a susceptibility. And if susceptibility is 0 in parallel branches, then it is considered as a resonance condition. Resonance condition. So therefore, this omega c minus omega L by R square plus omega square is equal to 0. And here I simplify this equation, and wherever omega is there, omega is equal to omega c. That is the resonance condition. So I got this is this resonant frequency for parallel circuit. Thank you.